Here we're going to be talking about the real number system and how to do some practice problems. Before we get into this, I really just want to describe how we're supposed to be using these videos. Everything I say, everything I write is important. I want you to be listening and writing everything that I write down. If I write something down, you should be writing it down too. If I say it and you think it's important, you could also write that down. You need to be listening to these and focusing on what I'm saying and writing, and if there's anything that you don't understand, stop us at that moment and ask us for an explanation. Most of the time we're going to use these videos during class, so you'll have teachers around where you can actually get help. You need to use them. Please don't just watch the video thinking that that's going to help you learn anything. You need to be active in this learning. So on this first example, we're trying to place these numbers into this diagram, into the real number system where they're supposed to go. So it's really important that we simplify each of these expressions before we decide to place it. Especially on that, like the second example, 26 over 13. That looks like a fraction, so you might think it's rational, but actually it's going to simplify to a much simpler number. You have to decide what that number is in its simplest form before placing it in a subset. This word, a subset. Subset really just means a smaller set inside a bigger set. So natural numbers are a subset of whole numbers because that circle is completely contained in that. So it's looking for the best subset, the best small group that you can fit each of these into. For negative 11.2, we see that that has a decimal part. Negative 11.2, you might see that it's a negative number, so you might be thinking that has to be an integer. But since we have a decimal piece, that 0.2 part, that is not a decimal, or sorry, that is not an integer, it's not a whole number, or its opposite. That is a rational number. On the second one, I'm just going to go straight down the first column. 18 is a whole number, it's positive, that's a natural number, it's one of the counting numbers. When you start counting, you'd say 1, 2, 3, 4, you'd eventually get up to 18. That's a counting number. Actually, let's just do it by this. Let's pick out all the natural numbers. Anything that's just a counting number. So I have 18. I know pi is not going to be 1. I know 4 divided by 5 is not a whole number. 15.0, that's really just the number 15. That actually doesn't have a decimal part. Even though there is a decimal point, there's no part that's actually a decimal. There's no leftover remainder part. It's just 15. 2 times pi, that's going to be a decimal. 26 divided by 13 is really just 2. That's a positive whole number. That one works also. That's 26 over 13. Negative 36 is a negative number. Negative square root of 200, also a negative number. 0, that is not a positive number. This one has a decimal. This one I'm going to change right away. It's 450%. A percent is just part of 100. That's really what percent means. We're going to divide that by 100. That's really 4.5. So that's also a decimal. It's not going to fit into the natural numbers. So I've gotten all of my natural numbers. The only whole number that can possibly go in here is 0. So I'm going to put 0 in there. There's nothing else that's a whole number, but not natural. This is the only thing that's actually going to go into that group. It's not the only whole number. Actually, 18 is also a whole number. It's a natural number, and the natural number circle is inside the whole number circle. All natural numbers are whole numbers. But the only one that can be called a whole number, but not a natural, is 0. Got that one also, note this one, note this one. Let's just take care of the ones with pi, because that is the easiest one to recognize. Anything with pi is a decimal that goes on forever and doesn't repeat. That has to be irrational. If I do 2 times pi, it's still irrational. That's going to be something like 6.28, going on forever, not repeating the same number over and over. That's still irrational. It doesn't matter if we multiply by 2, it's going to stay irrational. All right, 4 divided by 5 is 0.8. That's a decimal that stops. It's also a fraction, so we know that's fraction. Negative 36.0, it's kind of like the 15.0. That 0 really doesn't mean anything. It's just negative 36. That's a negative whole number. So that is a integer. negative square root of 200 would be the square root of 200, and then you change that into a negative. That's about negative 14.14 going on forever. It's not repeating 1414 over and over. It's just repeating random numbers over and over. Anytime you take the square root of something that's not a perfect square, you're going to get an irrational number. It's a decimal that doesn't repeat, and it doesn't stop. It has to do both of those things. If you did something like the square root of 16, that would fall into here. If you do the square root of 16, that's just 4, because 16 is a perfect square. The square root of 200 is not a nice number. It's going to be an irrational. The decimal 2.89582 goes on for a while, but it does stop. That's going to be rational. It's a decimal that stops. It can be written as a fraction. And negative 40.5, kind of the same thing. 450% is a decimal that stops. So it's rational. On the next examples, we're just trying to decide if it's rational or irrational. So there's going to be an operation happening. It's either multiplication, division, subtraction, or addition. And something's happening in between these two numbers. We just have to decide, is there an irrational number in there at all? If there is, it's automatically irrational. If they're both rational, then it's going to stay rational. These are two fractions. I have 1/7 and 1/3. It doesn't matter what that decimal ends up being. I know that fractions are rational. If I multiply two fractions, it's still going to be rational. That is a rational number. It's going to look like a weird decimal, but it actually does repeat. And it can be written as a fraction. Really, it can just be written as 1/21, so it has to be a fraction. This next one, B, is a weird example because we actually do have a fraction. Almost all fractions are rational, unless there's an irrational number in there. 7 is not a perfect square. I know it's going to be irrational. I do the square root of 7, it's going to be a decimal. I divide it by 10, it's still a decimal that goes on forever, doesn't repeat, that's irrational. Square root of 16 is a little bit different. That would give me 4/7. That's going to be a little bit of a weird decimal, but it actually repeats. I think it's the same 6 numbers over and over. And again, it's just a fraction with two numbers that are not irrational. That makes that rational. I have 14, that's rational. I have a decimal that stops, that's rational. I have a decimal that goes on forever. It's not the same number over and over. That's 6, then 5, then 4, then 0. It's different numbers. I'm going to end up adding 5 to this, but if that doesn't change it, I still have an irrational number, plus 5, it's still irrational. Next one, I see square root of 45. That's not a perfect square. I can immediately rule that out. Doesn't matter if I times it by 7. It's still irrational. I see pi. I'm going to mark that as irrational right away. Doesn't matter if I multiply times 5 and then subtract 8. It's still irrational. The letter H, the first one is a repeating decimal. This part is repeating. So that's rational. Plus a decimal that stops. That's rational. So that ends up as a rational number. Almost the exact same thing on the next one, except it's just two decimals that stop. Decimal stops, decimal stops. Those are both rational. Doesn't matter if I multiply them together, it's still going to be rational. On the last examples, we're trying to write always, sometimes, or never for each of these. Integers are rational numbers. I'm going to draw that chart again. I have my integers, then I have my rational numbers. Everything in here, everything in the integer square there, is also contained in the rational number square. For example, negative 3.0. That's an integer. 4.0. That's an integer. Those are both rational numbers. They're decimals that stop, and they can also be written as fractions. That will always happen. No matter what integer you have, it is always going to be rational. The opposite is not true. I can think of an example really easily. 1/2. It's rational, but it's not an integer. There's sometimes when it happens, though. These examples up here are examples where rational numbers are actually integers. but it's not every single time. That's a sometimes. Same thing with the next one. There's some negative numbers that are rational, but some are irrational, like negative 5. But negative 3.5 is rational. That happens sometimes. There's some negative numbers that are rational and some that are not. 0 is always going to be an integer. Actually, I'm going to go back up to this chart. Oops. 0 is in this circle, which is completely contained in the integer circle. Everything in a smaller circle is contained in the bigger one. So 0 is an integer, it's rational, and it's real. It is not natural. It's in the bigger circles, it's not in the smaller one of natural. That's why it is always, whole numbers are always integers. And the last one, irrational numbers are real. Well, all the numbers that we're learning about for now are real. Irrational, rational, they're all real. So that is always going to be true.